Okay, here's a pretty important point. This is the second movie in form tolerance lesson. Interrelationship between features is not affected by Rule 1. Boundary requirement does not require perfect orientation with respect to other features. If we have a model that's dimensioned like this, we have a thickness, we have a length, and we have a width, and we also have a a tolerance, a dimension with a tolerance applied on the right angles here. What does that mean? Okay, here would be an acceptable part that's produced. Okay, whereas if the part is made at the maximum material condition of the overall length, what we're looking at here is perfect form, where these sides are perfectly parallel and flat. Okay, and same with this 1.510 dimension. That's the maximum material condition of that. Okay, and so at the maximum material condition of that, these two sides have to be perfectly flat and parallel. But it does nothing for the angle here. So in this particular case, that angle could be like 90.5 within tolerance here. Okay, but in which case, our part's going to look like a parallelogram. So rule number one, boundary requirement does not affect the interrelationship between features. Perfect form. Perfect form boundary effect on flat surfaces. Okay, so here we have a 1 inch plus or minus 10 thousandths dimension. We know that, and per rule 1, that the feature must be a perfect form when it's at its MMC. What does that look like? Here we have our perfect form boundaries for the maximum material condition. And then if we have some actual variations here between the part dimensions and this perfect form boundary, it is going to fit as long as this part is within tolerance. Okay, so the maximum possible form variation equals the size tolerance. Okay, so this is very important. The maximum possible form variation equals the size tolerance. Okay, so from 990 to 1 inch and 10 thousandths, that is the possible variation, which happens to be plus or minus 10 thousandths. So maximum possible form variation equals the size tolerance. Okay, then finally, surface form variation cannot exceed the size departure from MMC unless an exception to rule number 1 is specified. We'll talk about that in a minute here. Perfect form boundaries effects on cylinders. The shaft perfect form boundary as a cylinder equals the maximum size or limits of the shaft. Okay, so in which case I have a shaft here. This is, again, if we're going to put a feature, if we're going to put one of these form tolerances on a feature of size. Okay, so what we're looking at here is we have a shaft which is 1 inch plus or minus 10 thousandths, and so our perfect form boundary here is going to be 1 inch 10 thousandths, and then our maximum variation is limited by the actual size variation, which is plus or minus 10 or 20 thousandths total. Shaft perfect form boundary, a cylinder equals the maximum size limit of the shaft. And then if we're talking about a hole perfect form boundary is a cylinder equal to the minimum size of the hole. So perfect form boundary would be, on a shaft, would be the maximum diameter, and then the hole, so the perfect form boundary of a hole would be the minimum diameter. In both cases, that's the maximum material condition. Let's talk about some exceptions to Rule 1. You can apply the tolerance with a free state modifier. That's one way to do it. Perfect form is not required in MMC is kind of like what that says. It applies to gaskets and stuff like that. Apply form tolerances for straight or flatness to features of size. That's another way that you would take an exception to Rule 1. And apply an independency symbol to a size dimension. We'll discuss what that means in later. And then really this exception to Rule 1 is really not applicable to bars and sheets and other stock materials. Okay, let's talk about free state versus restrained. All dimensional requirements apply in a free state condition. unless specified otherwise. Okay, so this is kind of new for GD&T 2018. We need it is assumed that you take your part, you manufacture your part, and you set it down on an inspection table, and all of the dimensions that you see on the drawing by default have to apply with that part just sitting there in its free state. Okay. Um, and why is that different? Well, in some cases, like a flimsy gasket or something like that, it could have some stresses in it and not sit particularly flat on a table. Well, in which case you'd probably want to constrain it or something like that to get the actual measurements. But all dimensional requirements are assumed to apply in the free state unless otherwise specified. Um, and if you want to, if you have to, you would specify an exception to that rule. And you can do that with a drawing note saying, hey, notation used to establish tolerances applicable when restrained. You could have a drawing note that says something like that, that says, I could have a form tolerance, and then I can have a profile tolerance, for instance, on the edges of a gasket part, flimsy gasket part. And a gasket part gets stamped out, and when you lay it on the table, it doesn't necessarily sit flat, due to all the manufacturing forces that went in to make it. And what I would say to do with that is, I would say all of the profile tolerances, I would add a note to the drawing saying all of the profile tolerances apply in the restrained condition. Okay. So the point here is all dimensional requirements apply in the free state unless otherwise specified. And if you want your tolerances to apply at a restrained state, for instance, you have to put a note there. Okay, important terms. He'll call this an important term, your author, but it's a new term. I don't want you to get too hung up on it. It's called an actual mating envelope, and it's kind of like that perfect form boundary. Is really all it is. And it's a theoretical perfect geometric shape in contact with a feature. So it does kind of represent the perfect form boundary, and it's called the actual mating envelope. An axis is exactly straight line at the center of the actual mating envelope. Okay, so in this case it's the cylinder part. Okay, and the actual mating envelope is a reverse cylinder. It's a hole, if you will. And the axis of that hole is a straight line at the center of that mating envelope. Now, the derived median line is a line made at the center of the points along the length of the feature. Say when we start talking about derived median line, we're talking about the part. Okay, so here's our part, and we have a derived median line, and that's a line made of the center points or midpoints along the length of the feature. And then line elements are always in one direction on the surface of a part. So let's start talking about what a straightness tolerance is. A straightness tolerance specifies how close to perfectly straight a feature must be made. Okay, again, this can be applied to a surface line element or a median line, derived median line. Okay, so if I was applying a straightness tolerance to a surface, it would be applied to a surface line element. Or if I applied the straightness tolerance to a feature of size, like a hole or a cylinder or a hole or a cylinder, that would be a derived median line. Okay, feature of size, derived median line, and then surface line element, that's for a surface feature. Okay, surface line elements or line on the surface of parts is in a single direction. You need to specify the direction of the straightness. Derived median line made of center points along all cylinder cross sections for the cylinder feature. What that means is you take the part and you'll take a derived median line of the part, and what you'll do is you'll find the center points at certain samples along the length of that part, and that becomes your derived median line. I'd like to end this movie right here, and we're going to continue talking about straightness for quite a few more slides. Okay, thank you.